Welcome to DAR Tutors for online and home tuition. In this video, we will explore a range of key concepts in electrochemistry and organic reactions, central to the IB Chemistry higher level syllabus. Specifically, our learning objectives are to compare voltaic and electrolytic cells, investigate electroplating, understand the oxidation and reduction of organic functional groups, and calculate and apply standard electrode potentials. We will begin by contrasting voltaic or galvanic cells with electrolytic cells. While both involve redox reactions, their fundamental functions are opposites. A voltaic cell converts chemical energy into electrical energy through a spontaneous redox reaction. This means the reaction proceeds on its own, releasing energy. Conversely, an electrolytic cell uses an external electrical energy source to drive a non-spontaneous redox reaction. Energy must be supplied for the reaction to occur, so it converts electrical energy into chemical energy. A key difference is the setup. A voltaic cell requires two separate half cells connected by a salt bridge and an external circuit to allow for controlled electron flow. An electrolytic cell, on the other hand, typically consists of a single electrolyte, which can be an aqueous solution or a molten salt, with two electrodes immersed in it. A crucial distinction lies in the role of the anode and cathode. In a voltaic cell, the anode is the site of oxidation and is the negative electrode. Electrons are released here. The cathode is the site of reduction and is the positive electrode, where electrons are accepted. Now, let's reverse that for an electrolytic cell. Here, the anode is where oxidation happens, but it is the positive electrode because it's connected to the positive terminal of the power supply. The cathode is the negative electrode where reduction occurs. So remember, oxidation always occurs at the anode, and reduction always occurs at the cathode, regardless of the cell type. What changes is their electrical polarity, which is determined by whether the cell is producing or consuming electrical energy. A direct application of the electrolytic cell is electroplating. Electroplating is a method used to coat one metal object with a thin layer of another metal. This is primarily done to improve appearance or prevent corrosion, such as chroming a car bumper or silver plating cutlery. To achieve this, the article to be plated is made the cathode in an electrolytic cell. A rod of the plating metal, say silver, is made the anode. The electrolyte must contain cations of the metal we want to deposit, so for silver plating, we would use a solution of silver ions. Let's look at the reactions. At the anode, the silver rod oxidizes, dissolving into the solution as silver ions. These ions then migrate to the cathode, the spoon, where they are reduced back to solid silver metal, forming a coating. The anode half reaction is silver metal forming silver ions and an electron. The cathode half reaction is a silver ion gaining an electron to form solid silver. There are some key considerations for successful electroplating. First, the object to be plated must be perfectly clean and free of grease. This ensures the deposited metal adheres properly. Think of it like painting. You need a clean surface. Second, to get an even coating, the object should be rotated during the process. This ensures that the concentration of metal ions near the surface remains consistent, leading to a uniform deposition. A third crucial point is the current. If the current is too high, the plating will occur too rapidly, leading to a furry or burnt deposit that is brittle and will flake off. A controlled lower current ensures a smooth, adherent coating. This is why complexing agents are often used. For example, in silver plating, the complex ion AgCN is preferred because it produces a very low, stable concentration of Ag+ ions. Let's work through an IB-style problem on electroplating. Imagine we are tin plating a steel sheet. The problem states that a tin coating of 1.0 times 10 to the power of -5 meters thick is often used for food cans. Let's calculate the volume in moles of tin needed for one side of a 1.0 meter by 1.0 meter steel sheet. The first step is to write the ionic equation for the reaction at the cathode. Tin is in group 14, and in a salt like tin sulfate, it will be in the +2 oxidation state. So, to become solid tin, the tin2 ion must gain 2 electrons. The equation is Sn2 plus aqueous plus 2 electrons gives solid tin. Next, let's calculate the volume of tin needed. The area is 1.0 times 1.0 biomass, and the thickness is 1.0 times 10 to the -5 mass. Volume is area times thickness, which gives us 1.0 times 10 to the minus 5 cubic meters. We need to convert this to cubic centimeters because the density is given in grams per cubic centimeter. There are 100 centimeters in a meter, so 100 cubed, or 10 to the power of 6 cubic centimeters in a cubic meter. Multiplying our volume by 10 to the 6 gives us 10 cubic centimeters. Now we can calculate the mass using the density of tin, which is 7.3 grams per cubic centimeter. Mass is density times volume. 7.3 grams per cubic centimeter times 10 cubic centimeters equals 73 grams. Finally, to find the moles of tin, we use the molar mass, which for tin is 118.71 grams per mole. Moles is mass divided by molar mass. 73 grams divided by 118.71 grams per mole gives approximately 0.61 moles of tin. This is the amount of tin that must be plated onto the sheet. We now turn our attention to voltaic cells, which convert spontaneous chemical reactions into electrical energy. A classic example is the Daniell cell. The Daniell cell consists of two half cells. On one side, a zinc electrode is immersed in a zinc sulfate solution. On the other, a copper electrode is immersed in a copper 2 sulfate solution. These are connected by a wire to an external circuit and by a salt bridge. Here you can see the arrangement. The salt bridge allows the flow of ions to maintain charge neutrality, and the voltmeter measures the potential difference, which we call the voltage. Since zinc is more reactive than copper, it readily loses electrons. This occurs at the zinc electrode, which is the anode, and the negative electrode. The copper electrode is the cathode, where copper ions from the solution gain these electrons and are deposited as copper metal. The salt bridge is a critical component of any voltaic cell, and it's a common source of misconceptions. A common mistake is thinking the salt bridge provides electrons. It does not. The electrons travel through the external wire. The salt bridge's role is to maintain electroneutrality in the two half cells. As zinc ions form in the anode half cell, there's a buildup of positive charge. Simultaneously, as copper ions are consumed in the cathode half cell, there's a deficit of positive charge. The salt bridge contains a solution of inert ions, typically potassium nitrate. Nitrate anions flow into the anode half cell to balance the excess positive charge, and potassium cations flow into the cathode half cell to compensate for the lost positive charge. This continuous flow of ions completes the circuit and allows the spontaneous redox reaction to proceed. Without a salt bridge, the charge imbalance would quickly halt the electron flow, stopping the cell. We can represent voltaic cells using a shorthand notation called a cell diagram. This is a concise way to describe the cell components. By convention, the anode half cell, where oxidation occurs, is always written on the left. The Daniell cell, for example, is written as solid zinc, single vertical line, aqueous zinc ions, double vertical line, aqueous copper ions, single vertical line, solid copper. Let's break this down. The single vertical line represents a phase boundary, separating a solid electrode from its aqueous solution. The double vertical line signifies the salt bridge. This diagram instantly tells us that zinc is oxidized at the anode, and copper ions are reduced at the cathode, connected by a salt bridge. It's a powerful tool for quickly understanding and comparing different electrochemical cells. Standard electrode potentials are central to the study of electrochemistry. They allow us to predict the spontaneity and voltage of a voltaic cell. The potential difference of a single electrode cannot be measured in isolation. To measure it, we need a reference point. This reference point is the standard hydrogen electrode, or She. The She is a platinized platinum electrode immersed in a 1.0 mol per cubic decimeter solution of hydrogen ions, over which hydrogen gas is bubbled at 100 kilopascals and 298 Kelvin. The electrode potential of this specific half cell is arbitrarily defined as exactly 0.0 volts. Every other half cell potential is measured relative to this standard. This allows us to create a table of standard reduction potentials. Here is a table of standard electrode potentials, often found in your IB chemistry data booklet. Notice that all reactions are written as reductions, that is, a species gaining electrons. By convention, the more positive the E naught value, the greater the oxidizing strength of the species on the left side of the equation. Conversely, The more negative the E naught value, the greater the reducing strength of the species on the right side. This electrochemical series tells us that lithium ions are the weakest oxidizing agent, while solid lithium is the strongest reducing agent. At the other end, silver ions are the strongest oxidizing agent, and solid silver is the weakest reducing agent. We use this table to predict the outcomes of redox reactions. Let's use a worked example to see how to apply this table. The question asks us to arrange several oxidizing agents in increasing order of their strength. The oxidizing agents are potassium manganate sulfate 7s, which is the permanganate ion iodine iron 3 ions, and oxygen in acidic solution. We find the corresponding half equations in the data booklet and write down their standard electrode potentials. An oxidizing agent undergoes reduction. Its strength is directly proportional to the E naught value of its half cell. A more positive E naught value means a stronger oxidizing agent, so we simply order them from the lowest E naught to the highest. Iodine has the smallest E naught at plus 0.54 volts, followed by iron F3 at plus 0.77 volts, then oxygen at plus 123 volts, and finally potassium manganate 7 at plus 151 volts. This is the order of increasing oxidizing strength. Now let's explore fuel cells, which are electrochemical devices that convert the chemical energy of a fuel directly into electrical energy. Unlike a battery, a fuel cell does not require recharging. It generates electricity as long as fuel is supplied. The most common is the hydrogen fuel cell. In a hydrogen fuel cell, hydrogen gas is fed to the anode, where it reacts with hydroxide ions from the electrolyte. At the cathode, oxygen gas reacts with water to produce more hydroxide ions. Combining these, we get the overall reaction. 2 hydrogen molecules react with 1 oxygen molecule to produce 2 water molecules. The flow of electrons through the external circuit provides the electrical energy. Fuel cells are not just limited to hydrogen. They can also use hydrocarbons or alcohols as fuels, which are often easier to store and transport. Let's consider an ethanol fuel cell. Here, ethanol is oxidized at the anode in the presence of water to produce carbon dioxide, hydrogen ions, and electrons. At the cathode, oxygen is reduced to water. The overall reaction is the combustion of ethanol. Unlike a hydrogen fuel cell, this one produces carbon dioxide, a greenhouse gas. This highlights that while fuel cells can be very clean, their environmental impact depends on the specific fuel used. A key advantage of fuel cells, particularly hydrogen fuel cells, is that they convert chemical energy directly to electricity, avoiding the Carnot cycle efficiency limits of heat engines and thus producing less waste heat. It's the 10-minute mark. If you find this lesson helpful and are looking for more expert tuition in IB, A-Level, or IGCSE, please contact our tutors. We provide personalized online and home tuition to help you succeed. Now let's continue with our lesson. We now move to a fundamental concept in organic chemistry, the oxidation of functional groups. The chemical characteristics of organic molecules are determined by their functional groups. Alcohols and aldehydes, containing hydroxyl and carbonyl groups respectively, are particularly susceptible to oxidation. The classic oxidizing agents for these reactions are sodium dichromate Vi and potassium manganate 7, both typically used in acidic conditions. These agents are transition metal compounds, and their color change is often a visual indicator of the reaction's progress. Let's first consider primary alcohols. The key here is the carbon atom to which the hydroxyl group is attached. A primary alcohol is defined as having its hydroxyl carbon bonded to only one other carbon atom. A secondary alcohol's hydroxyl carbon is bonded to 2 other carbons, and a tertiary alcohol's to 3, etc. Primary alcohols can be oxidized in 2 steps. First, to an aldehyde, and then, if conditions are vigorous, to a carboxylic acid. We represent an appropriate oxidizing agent with the symbol O. For example, ethanol is a primary alcohol. Mild oxidation produces ethanol, an aldehyde. If we heat ethanol under reflux with excess oxidizing agent, it is further oxidized to ethanoic acid, a carboxylic acid. This is the process that turns wine into vinegar. The beauty of organic synthesis is that we can control the outcome. By selecting the right conditions, we can stop the oxidation at the aldehyde stage. To obtain the aldehyde, we use a distillation apparatus. The aldehyde is more volatile, meaning it has a lower boiling point than the starting alcohol and the carboxylic acid product. The reaction mixture is heated gently. As soon as the aldehyde forms, it boils and distills off into a receiving flask, escaping the oxidizing agent. This prevents it from being oxidized further to the carboxylic acid. This technique, simple distillation, allows us to isolate the intermediate aldehyde. For mixtures with boiling points that are close, such as ethanol and ethanol, we use fractional distillation with a fractionating column to achieve a better separation. The column provides a large surface area for repeated evaporation and condensation, leading to a purer product. To produce the carboxylic acid, we need to ensure the aldehyde is fully oxidized. We do this using a technique called reflux. In a reflux setup, the reaction flask is heated and a condenser is mounted vertically above it. The hot vapor rises, condenses in the cool condenser, and then drips back into the flask. This allows the mixture to be heated at its boiling point for an extended period, without any loss of volatile reactants or products. Heating under reflux ensures that all the alcohol and the intermediate aldehyde stay in contact with the oxidizing agent until they are completely converted to the carboxylic acid. Using an excess of the oxidizing agent further guarantees full oxidation. In summary, distillation allows us to produce aldehydes by removing them as they form, while reflux allows us to produce carboxylic acids by keeping the reactants and intermediate in the reaction mixture. The type of alcohol also dictates its oxidation products. Let's look at secondary and tertiary alcohols. In a secondary alcohol, the hydroxyl carbon is bonded to one hydrogen and two alkyl groups. When oxidized, this hydrogen is removed along with the hydroxyl group, forming a carbon-oxygen double bond. The product is a ketone. A classic example is the oxidation of propan-2-OL to propanone. Critically, ketones do not have any hydrogen atoms on the carbonyl carbon and cannot be oxidized further under these conditions. Tertiary alcohols, where the hydroxyl carbon is bonded to three alkyl groups, cannot be oxidized by acidified dichromate or manganate 7 at all. There is no hydrogen atom on the hydroxyl carbon to remove, and breaking the carbon-carbon bonds would require much more vigorous conditions. A well-known application of alcohol oxidation is the chemical breathalyzer. Though no longer in use, it illustrates the chemistry perfectly. The device contained acidified potassium dichromate, VE, an orange oxidizing agent. When breath-containing ethanol passed through the tube, the ethanol was oxidized to ethanoic acid. Simultaneously, the orange dichromate ion was reduced to a blue-green chromium-3 ion. The overall reaction shows orange dichromate VI becoming blue-green chromium-3. The extent of the color change along the tube was proportional to the concentration of alcohol in the breath. Modern breathalyzers are more sophisticated. Fuel cells are often used, where the current produced by the oxidation of ethanol is measured. More advanced versions use infrared spectroscopy to accurately identify and quantify ethanol. Just as we can oxidize functional groups, we can also perform the reverse reaction. Reduction. Reduction is the gain of hydrogen, the loss of oxygen, or the gain of electrons. Two powerful complex hydride reagents are commonly used for reduction in organic chemistry: lithium aluminum hydride and sodium borohydride. Both reagents act as sources of the nucleophilic hydride ion, H-. Lithium aluminum hydride is more reactive and hazardous, requiring completely dry conditions. Sodium borohydride is safer, easier to handle, and can be used in aqueous or alcoholic solvents. Sodium borohydride can reduce aldehydes and ketones to their corresponding alcohols. Aldehydes become primary alcohols, and ketones become secondary alcohols. Lithium aluminum hydride is a stronger reducing agent. It can reduce aldehydes and ketones, but it also has the power to reduce carboxylic acids and their derivatives, like esters, amida, and nitriles, to alcohols or amines. Let's work through a problem to see this in practice. The question asks for the structural formulas of compounds produced when several organic molecules are reduced with lithium aluminum hydride. Part A is pentan 2,1. This is a ketone. Remember, ketones reduce to secondary alcohols, so pentan 2,1 becomes pentan 2-ol. Part B is 2-methylpropanol. This is an aldehyde. Aldehydes reduced to primary alcohols. The product will be 2-methylpropan-1-OL. The aldehyde functional group at the end of the chain becomes a primary alcohol. Part C is ethanoic acid. Carboxylic acids reduce to primary alcohols, so ethanoic acid becomes ethanol. For Part D, we have a keto acid. This molecule contains both a ketone group and a carboxylic acid group. Lithium aluminum hydride is a strong, non-selective reducing agent for carbonyls. It will reduce both the ketone to a secondary alcohol and the carboxylic acid to a primary alcohol. The product will be a diol with a primary and a secondary alcohol group. Notice that LiAlH4 is so powerful that if you try to reduce a carboxylic acid to an aldehyde, you cannot stop the reaction at the halfway stage. The aldehyde would be immediately reduced further to the primary alcohol. In this example, we'll draw a circle on the screen. Then we'll shift it to the left. Finally, we'll change it to a square. Here is some text on the left side. And here's a mathematical expression. Let's clear the text content from the screen. End of demo. We have covered a significant portion of the electrochemistry and organic reactions in the IB/HL chemistry syllabus. We've compared voltaic and electrolytic cells, explored the practical application of electroplating, and analyzed the oxidation and reduction of key organic functional groups. To consolidate your understanding, let's work through 5 IB-style practice questions. Pause the video and try them on your own before watching the solutions. Question 1 asks you to consider the following standard reduction potentials. Part A asks for the structural formula of the alcohol that is oxidized to form propanone, and to name the alcohol. Part B asks you to determine which species from the list is the strongest oxidizing agent, and to justify your answer using the E0 values. And Part C asks you to construct a voltaic cell from 2 of these half cells to produce the maximum voltage. Write the half equations and the overall cell reaction, and calculate the cell voltage. Take a moment to work through this. Let's review the solution for question 1. For Part A, propanone is a ketone. Ketones are formed by the oxidation of secondary alcohols, so the alcohol must be propan-2-OL. The structural formula has 3 carbons with a hydroxyl group on the central carbon. For Part B, the strongest oxidizing agent is the species on the left of the half equation with the highest, most positive E0 value. Looking at the table, the permanganate ion has an E0 of plus 1.51 volts, which is the highest. Therefore, permanganate is the strongest oxidizing agent. For Part C, to get the maximum voltage, we need the largest difference in E0 values. This would be the permanganate half cell at plus 1.51 volts and the iron half cell at 0.45 volts. The higher E0 value will be the reduction, and the lower E0 value will be the oxidation. So permanganate ions are reduced to manganese II ions at the cathode. Iron is oxidized to iron II ions at the anode. To get the overall reaction, we balance the electrons by multiplying the anode reaction by 5 and the cathode reaction by 2. This gives the full, balanced redox equation. The cell voltage is the difference between the reduction potential and the oxidation potential. So, plus 1.51 minus 0.45 equals plus 1.96 volts. Question 2 asks you to draw the repeating units of the products of the complete hydrogenation of styrene, which is phenylethene. You also need to state the catalyst used and the type of chemical reaction. Styrene is phenylethane. It has 2 parts, a benzene ring, which is an aromatic part, and an alkene part, the ethene chain. The question specifies complete hydrogenation. This means reducing all possible sites. In the context of hydrogenation, unsaturated usually refers to C+C or CC bonds, as these are the ones that are easily reduced. First, the carbon-carbon double bond in the ethene chain will become a single bond. The benzene ring will also be reduced to a saturated cyclohexane ring. The repeating unit is therefore the saturated side chain attached to the ring. This is a polymer of completely saturated ethylbenzene. The catalyst used for hydrogenation is typically a transition metal like palladium or nickel. The reaction type is addition, specifically electrophilic addition or simply hydrogenation. Question 3 involves an unknown organic alcohol. It asks you to propose the structural formula of an alcohol, with the molecular formula C4H8O that can be oxidized by acidified potassium dichromate to produce a carboxylic acid. It also asks you to name the alcohol and the carboxylic acid. The key information here is that the alcohol is oxidized to a carboxylic acid. This tells us the alcohol must be a primary alcohol. Remember, secondary alcohols oxidize to ketones, and tertiary alcohols do not oxidize to carboxylic acids. We need a primary alcohol with 4 carbon atoms. The only primary alcohol with this molecular formula is butan 1-OL. So the alcohol is butan 1-OL. When this primary alcohol is oxidized to a carboxylic acid, it produces butanoic acid. The reaction shows the oxidation of butan 1-OL all the way to butanoic acid. This reaction would be performed under reflux with an excess of the oxidizing agent. Question 4 asks you to draw and name the major organic product of 2 reactions. Part A is the reaction of ethanoyl chloride with ammonia. Part B is the reaction of 2-bromopropane with aqueous potassium hydroxide. For Part A, ethanoyl chloride is an acyl chloride. Acyl chlorides undergo nucleophilic addition-elimination reactions. Ammonia acts as a nucleophile, attacking the electrophilic carbonyl carbon. The product is an amide, specifically ethanamide, along with a molecule of ammonium chloride. For Part B, we have a secondary halogenalkane reacting with a nucleophile, aqueous potassium hydroxide. This is a classic SN2 or SN1 reaction, leading to substitution. The hydroxide ion substitutes the bromide ion, resulting in the formation of a secondary alcohol, propan 2-ol.